Hey, welcome back everyone. So last time we covered a lot of linear algebra review. So we talked about matrices, so that's inner, outer products, transpose, so these are the basics. We talked about matrix rank, inverse, and the interpretation of diagonal and orthogonal matrices. And then we went a bit more advanced and we talked about singular value decomposition, including the interpretation of SVDs. And then we introduced eigen decomposition as a special case of SVD. So the special case would be eigen decomposition of symmetric matrices. And after that, we also talked about eigen decomposition in general. So when the matrix is not symmetric. And then we kind of continued on and talked about relationship between SVD and eigen decomposition. And then finally, we talked about norms of vectors and matrices, as well as matrix definiteness, right? So that was the positive definiteness, negative definiteness, and positive semi-definiteness and negative semi-definiteness, right? So that was, sorry, that's the, so that was from last time, right? So for I guess just to quickly recap the positive semi-definiteness and positive definiteness, basically in order to assign a sense of negativity or positivity to matrices, we use the notion of positive or negative semi-definiteness. And basically we look at all of the eigenvalues of the matrix, not the individual elements of the matrix. So that's important. So eigenvalues are what's important. Okay, and in matrices, we could actually have indefinite matrices. So that was not true for scalars, right? But for matrices, if some of the eigenvalues are positive, some negative, then the matrix would be indefinite. Okay, and then the symbols we use basically look like greater than or less than, except that they're kind of curly. And then we have the ones with equality as well. For Taylor expansion, we kind of went through this pretty quickly. Hopefully you guys, again, have seen this. But I think this slide kind of illustrates things in a nice way, with the blue function being the one that we're trying to approximate. So that's g of x. And then the red polynomial, which is the Taylor expansion about x equals 0. And as we have higher and higher order approximation, the approximation becomes more and more accurate. Last time I talked about how to verify, well, last time I just said that you can verify that for the 0th order expansion, the function values match, right? I guess that one you can do just by inspection. So at x0, in this case 0, we know that the value matches. So if you plug in g of x equals 0, well, as long as you set f to be the right constant, then the function value would match. For the first order approximation, we have to take the previous part and then add on this part. Right? Just want to quickly verify that if we take the derivative of the right hand side, we indeed get the derivative of g at x0. So basically, if you take a derivative, the variable is x, and well, if the variable is x, then this is a constant, so that goes to 0 when you take the derivative. Okay, secondly, in the second term, we simply have a term linear in x. So the only thing that will come out is going to be f prime of x naught. Okay, so then the derivative matches. I think I said something wrong a bit earlier. G of x is actually the approximation, and f is actually the function that we're trying to approximate. So basically, you can see that if you take the derivative of the right-hand side, or of g, I guess, then you do get exactly f prime of x naught. So that means that we're matching the first derivative of f. You can do a similar thing for the second one. Basically, again, remember that the variable is x. If we take derivative twice, then the first two terms will go to 0 because they're polynomials of less than degree 2. So the second term will be the only one that becomes non-zero. The 2 will come down once to cancel with this 2 here. And then if we take another derivative, what we would have is just f double prime. So, okay, so then that means that our second derivative matches. Okay, so let me do the second one quickly. So g of x is our approximation of f, and the second order approximation is f naught plus 1 over 1 factorial x minus x naught f prime of x naught plus 1 over 2 factorial x minus x naught squared f double prime of x naught. Okay, so if you take the first derivative, so let me actually, so we're going to do, I guess, three things, right? Let's check the function value. So if we plug in x naught, we'll see that g of x naught would be equal to f of x naught plus 0, because we have x minus x naught here, and then plus 0 again, because we have x minus x naught, right? So the function value matches. So value matches. Right, now you can kind of see the purpose of this x minus x naught appearing everywhere in every term, except for the first term. So let's take a look at the derivative. If we take the first derivative, the first term becomes 0, because the first term is a constant. The second term is a linear term, so the only thing that involves x is actually f prime of x naught. And then the last term, for the last term, we're going to get the 2 coming down to cancel with the 2 factorial. So that's going to give us x minus x naught. And then we still have this f double prime of x naught. So now if you plug in x naught into g prime, then we would just simply have f prime of x naught, because the second term still has an x minus x naught remaining, right? So that becomes 0 when you plug in x naught. So the first derivative matches. Okay, and finally, just very quickly, doing the second derivative. So then we start from g prime of x, take its derivative. The f prime of x naught is a constant because it doesn't involve x, so that becomes 0. And then the second term, the only thing multiplying x is going to be f double prime of x naught, right? So here again we have that the second derivative matches. Okay, so hopefully that gives you a very quick idea of why these are the Taylor expansions of f up to the second order. And if you have third order and so on, you basically just have 1 over a larger number factorial, and then x minus x naught to a larger power, multiplied by higher and higher orders of the derivatives of f. Okay, but then hopefully you can see the pattern. So let's move on. So in machine learning, a lot of times the input is going to be a vector, meaning that there will be multiple components in the input. And so we need to talk about polynomials in multiple variables. So here's one of the simpler ones. So here we have g of x1 comma x2. We're going to write down first all the constant terms for a polynomial of multiple variables. And then we're going to write down all the linear terms. Previously, if we only had one variable, there would be only one linear term. But we have two variables here, so we have two linear terms. Terms linear in x1 and x2. Next, we're going to write down the quadratic terms. So this means that any term which involves two of these input variables multiplied together. So that includes x1 multiplied by itself. So that's going to be two variables multiplied together. And then we have the x1, x2 term and the x2 squared term. Again, contrasting with the scalar case, if the input only, if the number of inputs is only one, meaning the input is a scalar, then we would only have one quadratic term. But now actually we have three quadratic terms. As you can see, or as you can imagine, if we have more variables, like 5, 10 variables, writing this down can be a bit cumbersome. So we're going to be using vector notation, or vector matrix notation actually. So we're going to write down x vector as x1, x2. So instead of writing g of x1 comma x2, we're just going to write g of x vector here. And the way you write it is going to be a constant alpha plus x transpose beta. So the beta is actually also a vector. I will fix that in the notes. Okay, so let me just remind myself to fix this. So b should be a vector. So now it looks more similar to the scalar case, right? Only one linear term. And then there's also going to be just one quadratic term, and that is going to be x transpose gamma x, where gamma is actually just a symmetric matrix. If you multiply this out, you will get all the terms here. Okay. So now Taylor expansion for a function of multiple variables, or simply a function of a vector. So this is going to look very much like the previous scalar case, now that we're using the vector notation. So the zeroth order is simply going to be g of x equals to f of x naught. You simply plug in x naught. So that's the same as what we saw over here. The first order Taylor expansion looks very similar. We still have the previous constant part, and then plus x vector minus x naught vector transpose what's called a gradient of f. So this is the analog of the first derivative of f in the scalar case. And then the second order is going to be what we had before, what we had above, plus 1/2 x minus x naught transpose, and then this what's called the hessian of f, and then times x minus x naught. So we have a constant term, a linear term, and then we have a quadratic term, right? So now this kind of looks like a quadratic expression, because previously we've seen that the quadratic term involves a vector transpose times a matrix times a vector. So this is exactly what this is, right? So vector transpose, the hessian is actually a matrix, and then multiplied by a vector without the transpose. Okay, so now kind of looking at it a little bit closer, I mentioned that this term, partial f partial x, that's the gradient. So the gradient is actually just a vector of all the partial derivatives of f with respect to all the components of x. So previously in the scalar case, I will try to not go back to the scalar case too often, but previously for the scalar case, we just had the first derivative. So that was pretty simple because f was only a function of one variable. So now that f is a function of multiple variables, i.e. a function of a vector, we now can take the derivatives with respect to all of the components of that vector. So that's why the gradient is actually going to be a n/1 vector. And that's why we needed a transpose here. So this is really an inner product. Now take a look at the hessian. Sorry, before that, so one interpretation of the gradient is the direction of steepest ascent. So in this two-dimensional case, we have x1 and x2, and then the vertical axis represents the value of f. Right? So suppose we have a function f that looks like this bowl here. Then the direction of the steepest ascent, so the direction that the function is going up the fastest, this direction, would be the gradient of f. And behind this bowl-shaped function f, we have the linear approximation, i.e. the first order approximation of f. So that's just the plane with the gradient matching this point, and also the value matching this point, of course. So the tangent plane. Okay, moving on to the hessian. So the hessian is actually taking the gradient. So the notation is going to be a bit confusing, but here's how you remember it. So first you remember that the gradient is just a column vector of all the partial derivatives of f. And what you do is you expand each of the elements of the gradient, and you take the partial derivative of each of the partial derivatives with respect to all the components of x. So for example, for the first component, partial f partial x1, this in general is going to be a function of x, all the components of x. So that means that we can take another partial derivative with respect to all the different components, right? So the way we write that down would be partial squared f over partial x1. This means that we take the partial derivative with respect to x1 twice. And over here, we take the partial derivative with respect to x1 and then take the partial derivative with respect to x2. Okay, so then basically each row here expands into n elements, each involving another, each involving the second, another derivative with respect to all the components of x. It turns out that it's a calculus fact that the order of differentiation doesn't matter. So for example, if you differentiate with respect to x2 and then x1, it's actually the same as if you did that first with respect to x1 and then x2. So the Hessian is always a symmetric matrix. Okay, so a function that looks like this, right? So basically a function that looks like that. So the last term of the second order Taylor expansion, written more simply, g of x equals x transpose ax. This is known as a quadratic form. And we can actually use the quadratic form to provide an alternative definition of positive or negative definiteness or semi-definiteness of the matrix in the middle. So positive definiteness means that for any x that is not equal to 0 that you plug into this expression, the result will always be positive. So that's positive definiteness. And if the result is always negative, then the matrix A would be negative definite. And then we have the corresponding definitions for semi-definite. We just add an equal sign to the inequality. And for the indefinite case, it just means that there exists x such that the quadratic form is positive, and also there can be another x such that the quadratic form is negative. So it turns out that this definition and the previous one are equivalent. Maybe one thing, kind of interesting thing to note, if you're trying to get back at familiarizing yourself with vectors and matrices. So if you look at this quadratic form, if you multiply a times x, you get a vector that is the same dimension as x, right? So A is a square matrix, so AX would have the same dimension as x. So now you take x transpose, a vector of the same dimension as x, that gives you a scalar. So quadratic forms are actually scalars. So that's why we can simply write greater than and less than. That's also why we can add everything together, right? We have scalar plus inner product, which is a scalar, and then plus quadratic form, which is also a scalar. Okay, just something to note. Maybe, hopefully, that will help bring back memories of vectors and matrix multiplication. Okay, let's move on. So let's now look at what quadratic forms look like. Actually, before that, kind of getting ahead of myself, we're gonna first look at maybe convincing ourselves a little bit that the two definitions of positive and negative definiteness and semi-definiteness, they match. Okay, so let's take a look at an indefinite case. So here, consider this A matrix, which is diagonal with 0.9 and negative 0.5. we can also rewrite this matrix as identity times the matrix times identity transpose. And the point of doing that is to kind of make the expression look like an eigen decomposition. So remember, with eigen decomposition, we needed a matrix. We needed an orthogonal matrix on the left and on the right, while identity matrix is actually orthogonal. So basically, this expression is this expression is the eigen decomposition of A. So that means that we can directly read off the eigenvalues. They're going to be 0.9 and minus 0.5. Because one of the eigenvalues is positive and the other eigenvalue is negative, the A matrix here should be indefinite. So that was according to the earlier definition. Okay, what about the new definition? For the new definition, we have to look at this quadratic form, x transpose ax. And as I just mentioned on the last slide, this is actually an inner product between x and ax, right? Ax is just a vector of the same dimension as x. Okay, so recall that inner products are positive if the arguments are less than 90 degrees apart, and they are negative if the arguments are more than 90 degrees apart. So the question is, after you multiply a to x, does the result become more than 90 degrees apart or less? Well, let's take a look. So this is a similar animation as before. We take a bunch of points and then we try to kind of multiply by a in slow motion in some sense. Again, we have also looked at the interpretation of diagonal matrices, right? So we know that the first component will be kind of multiplied by 0.9. So that's why along the horizontal direction, you can kind of see over time, the points are shrinking a little bit, right? So right now they're from -4 to 4. Over time, they shrink a little bit. And then the second component actually gets multiplied by -0.5. That means that they will actually flip signs. So we can see that some vectors will end up pointing opposite or very far from the original vector. Whereas sometimes, depending on what you plug in, the vector might be pointing in the same direction, but just a bit shorter. So this means that the result of this quadratic form is sometimes positive and sometimes negative. That means that, again, the matrix A is indefinite. So basically, the two definitions agree. Okay, so if we want to just write this down mathematically, we can consider these two vectors. The horizontal one will be scaled by 0.9, and then the vertical one will get flipped around and also scaled by 0.5. Right, so now if x is this one, is the horizontal vector, then the result will simply be 0.9. Right, you can, I encourage you guys to work it out at home. So E1 would be 1, 0, the standard basis, and at E2, if you plug in 0, 1, then the result is actually 0.5. So next, we're going to take a look at what the quadratic form looks like. So what exactly is the quadratic form, right? So remember that we're going to be plugging in two variables in this case, right? So x is a vector of multiple components. Let's just say 2 components for now. So we plug in any x1, x2. In the plot, it looks like x and y. And then we want to plot the value of x transpose ax as in the z-axis. So when a is positive definite, the quadratic form actually looks like a bowl. So it's actually a paraboloid. You can see that because everything starts at 0 and the whole thing opens up, there is no x that you can plug in other than x equals 0, such that the result is 0 or less. right? So this quadratic form is always greater than 0. And in the other direction, we have that when a is negative definite, the quadratic form looks like an upside down paraboloid. So a paraboloid opening down. Again, no matter what x you plug in, the value will always be negative, except for when x is 0, in which case you get 0. For the semi-definite cases, what happens is that you don't really get a paraboloid that actually is closed on all sides, right? So you get a parabola in one of the directions, but in the other direction, you may get a flat. The other direction is kind of flat. This means that x transpose x is greater than or equal to 0 for all x. So for example, this point here, you could plug this point in and you would get 0. And that point is actually, that value of x will not be 0, right? So this is the main difference between positive definite and positive semi-definite. For positive definite, the only way to get 0 is plugging in the origin. For positive semi-definite, you can actually plug in some other vector other than the origin, and you would still get 0. Okay, similarly for negative semi-definite a, we have kind of a parabola opening down, and the function is only a parabola in one of the directions, but not in others. If you have more variables, then some directions are paraboloids and other directions are flat. And finally, for a being indefinite, the quadratic form looks like a parabola that opens up in some directions and a parabola that opens down in other directions. Okay, so now we're going to do a bit of in-class review. So maybe take 2 to 3 minutes and look at this, true or false. Okay, let's take a look. So a linear combination is a special case of affine combination. So that's actually false. Actually, affine combination is a special case of linear combination. So is convex combination as well. So that means the second one is true. Next, a linear combination of vectors has the same number of dimensions as the vectors. So that's definitely true because linear combination just means multiplying each of the vectors by a scalar. That doesn't change their dimensions. and then adding up all the results. So that also doesn't change the dimensions. Okay, last one. A vector in a linearly independent set of vectors cannot be written as a linear combination of other vectors. Okay, so this one is true. So maybe we can take a look at this a bit more closely. Okay, so suppose you have a linearly independent set of vectors. Let's keep it simple and let's just do 3 vectors, right? All linearly independent. And I guess we can do this by contradiction. Suppose we can write one of the vectors as a linear combination of the other. So suppose v1 can be written as a linear combination of the other. So let's say a2 v2 plus a3 v3 for some a2 a3. Then we can actually move the v1 to the right side. So subtract v1 from both sides. And what we would have is negative v1 plus a2 v2 plus a3 v3 equals, let me actually just be completely clear and put all the arrows above every vector. Okay, so last step, minus v1 plus a2 v2 plus a3 v3 equals the 0 vector. But then this is a contradiction because we initially assumed that v1, v2, and v3 are linearly independent. Yet we found a set of coefficients, minus 1, a2, a3, such that this linear combination gives us 0, right? So then this means that the 3 vectors are not linearly independent. So this is a contradiction. So if we go back to the slides, the last part, the last one would be true. A vector in a linearly independent set of vectors cannot be written as a linear combination of other vectors, because if we could, then the vectors would no longer be linearly independent. So that's what we just showed. Okay, let's move on to the next one. So again, second question for in-class review. So please take 2 to 3 minutes and have a look. Okay, let's take a look at these. Any vector in a subspace can be written as a linear combination of the basis vectors for that subspace. So that is true. That's the definition of basis. Next, all basis vectors must be linearly independent of one another. That's also true, basically also from the definition of basis vectors. Okay, C. Any linearly independent set of vectors must be a basis. So this one is actually a little tricky, but it's actually true. I guess what I didn't say is what is it a basis of, right? So let's say that we're in 3D space and we only have two linearly independent vectors. So these two vectors would not be a basis for the entire 3D space, but it would still be a basis for whatever 2D subspace that they span, right? So this one is true. Okay, it is possible for a basis to have non-orthogonal vectors. That is true. So the only requirement is that they must be linearly independent, the basis vectors. Okay, and the last one, any orthonormal basis must be an orthogonal basis. Okay, that one is also true. So orthonormal is basically a special case of orthogonal, where all of the vectors are have a norm of 1. Okay, so hopefully you got these. And we're going to move on to 2 more. The next one here. Yeah, take 2 to 3 minutes. Okay, let's take a look. The outer product of two vectors is the transpose of their inner product. So that's definitely not true. So the outer product, so I mean there are many ways of showing this, but we just have to find one counterexample. So in general, we know that inner products will give us a scalar, but outer products gives us a matrix, right? So now if you take a transpose of this scalar, you're never going to get a matrix. So the first one is false. Okay, next, the transpose of a matrix is itself. That is true, right? You flip the matrix over, you flip it again, you get back the original matrix. Okay, next, AB all transpose is not necessarily the same as A transpose B transpose. So this one is, so this one is definitely false. Sorry, they're not necessarily the same. So then the statement is true, right? And then we can also easily find a counterexample as well. Okay, but in general, what would be true is that A B transpose, so A B all transpose would be the same as B transpose A transpose. We have to do them backwards. You can definitely come up with some very simple examples where, let's say A could be, let's say 1 by 3, so a row vector, and B is 3 by 1. So then when you multiply A and B, you just get a scalar, and when you transpose, you get a scalar. On the other hand, we said that A is a row vector, right? So 1 by 3. So if you have a 1 by 3 matrix here, you take a transpose, you get a column matrix, you get a column vector, or 3 by 1. And then the B matrix used to be a column vector, now it becomes a row vector, right? So now this looks like an outer product. So maybe I can quickly write it down actually, so it's not so confusing. So let's say that A could be, let's say some row vector, and then B could be a column vector of the corresponding size, right? So AB will look something like this. So that's a scalar. When you transpose it, you get another scalar. And then if you do A transpose B transpose, well, A transpose looks like a column, and then B transpose looks like a row, right? So you can kind of see that these are definitely not the same, right? Kind of goes back to the previous example as well. Okay, so let's keep going. Okay, so the outer product of a vector with itself must be a matrix, a square matrix. So that's definitely true. Outer product means that you take a vector and then you multiply by its transpose. So for example, yeah, let's write it down again quickly. So for example, you could have A could be a vector. By default, vectors are columns, right? So the outer product just means you take A and multiply by A transpose. Sorry about that. Okay, how do I erase this? Okay. Okay, A transpose. That's going to give you, again, column vector multiplied by row vector. And then that's going to give you a matrix. Okay, and in fact, it's a square matrix because the number of columns here is just going to be the same as the number of rows here is going to be the same as the number of columns here. So the resulting matrix will always be square. Okay, last one. The inner product of two vectors of different dimensions cannot be computed. Right, that is true. So in general, the number of columns of the first matrix or vector you multiply, that you're multiplying, must be the same as the number of rows in the second vector or matrix. Okay, so maybe again writing it down, right? So in general, if you want to multiply any two vectors or matrices, right? Let's say the first matrix is this one, and then the second matrix must look like this because we have to go along the rows. We have to go along each row, meaning go across the columns, and then go down the rows, meaning go across the first column of the second matrix at the same time. So the number of elements of the number of columns here must be the same as the number of rows. Otherwise, you cannot multiply them. So applying this to two vectors, it just means that if you have a vector and you transpose it, the number of elements must match the number of elements of the second vector, right? Because inner product is the same as first vector transpose second vector. Okay, so last one then. Take 2 or 3 minutes. I'll probably give you guys 3 minutes. Okay, let's take a look. First, left singular vectors are not necessarily the same as right singular vectors. So that's definitely true. We just saw an example. Okay, so next, right singular vectors could be the same as eigenvectors. So that is also true. If you look back at the previous slide, the slide that talks about how to go from SVD to eigen decomposition. So sometimes the U matrices are actually the same in the eigen decomposition as well as the SVD. Okay, singular values of the matrix always exist. Right, so that's always true. We can always take the SVD of any matrix, and then the middle sigma matrix will have all of the singular values. They're all non-negative, and they could all be zero as well if your matrix is a zero matrix. Yeah, but in general, you will have some non-zero diagonal elements. Okay, and then that also makes the next statement true, right? Singular vectors are non-negative. Okay, last one. Left singular vectors could be the same as right singular vectors. So this one also true. And to see this, we basically have to again look at the slide on SVD, going from SVD to eigen decomposition. So in the case of symmetric matrices, if you recall, the eigen decomposition looks like U and then lambda in the middle, and then U transpose, right? So if the lambda has all positive elements, then that would be the same as the sigma matrix in the SVD. And then because you have U on the left and U transpose on the right, you would basically have the same left singular vectors and right singular vectors, right? So yeah, so sometimes we may have U and then lambda and then U transpose. So this could be the eigen decomposition. If lambda is also all positive, then this is also the SVD as well. So in this case, we have the same left and right singular vectors. Okay, so that's it for today. Have a good weekend and see you guys next time.